Yep. Okay, 5B. Okay, so it's 3 meters between the mailbox and where the guy starts. And then it's 7 meters between where the guy starts and front door. And he walks to the front door in 10 seconds and then goes back to the mailbox and then goes back to the front door. Okay, so that's what the path looks like. For part B, the 0 position is where the man starts, so this is labeled 0. The positive direction is towards the mailbox, so that's positive. And so to label those other 2 points, if you start at 0 and go 3 meters in the positive direction, you're at positive 3 meters. And if you start at 0 and go 7 meters in the negative direction, you're at negative 7. The 0 time is 10 seconds before he starts walking. So this point here is at 10 seconds. And it takes another 10 seconds to get here, so this is 20 seconds. Then it takes 15 seconds to get back to the mailbox here, so that's 35 seconds. And then it takes 20 seconds to get here, so this is 55 seconds. Let me know if you have any questions as I'm going through. And so now we can make the table. So at time 10 seconds, the position is 0. At time 20 seconds, the position is negative 7. At time 35 seconds, the position is positive 3. And at 55 seconds, the position is negative 7 again. So there's 3, there's negative 7, here's 10, 20, 35, and 55. And the points on the graph that we know, at 10 seconds, we're at 0 position. At 20 seconds, we're at negative 7. At 35 seconds, we're at positive 3. And at 55 seconds, we're back at negative 7. And so it looks like that. Any questions about that? Any other problems on the test you want to see? Okay, so the last thing we talked about, so last time we started talking about free fall. And when I say free fall, I'm talking about things falling straight down and things that are like launched into the air. So this includes projectile motion. Um, and I talked about the things that change the effect of air resistance on an object's motion. So how massive the object is matters, how much surface area it has matters, and how fast it's going. Those are the things that affect, that determine air resistance effect on the object's motion. And so if first the object isn't touching any other, isn't touching anything, and two, we can assume that air resistance is negligible. Air resistance has a negligible effect on the object's motion. So if those two things hold, then we can treat the object as being in free fall. And when that's the case, the object has a downward acceleration of g, lowercase g, and that's equal to 9.81 meters per second squared. That's what we expect near the surface of the Earth. You can do free fall problems on the moon or whatever. It works the same way, but then you have a different acceleration. Okay, so let's use that in a problem. So let's say you're walking across a bridge and you want to know how tall it is. You don't have a tape measure that long. Here's the water. But you find like a rock or something that you don't expect to have to be affected very much by air resistance. You're bald because it's easier to draw. Okay, and so you just take this object, drop it down to the water, time how long it takes from when you release it to when it hits the water. And let's say that it takes 1.2 seconds for the rock to hit the water after it's dropped. How high is the bridge? You can do this to measure the height of things, but look for boats or whatever before you do it. Or don't give them my name. Okay, so this is a constant acceleration problem. So we're going to do it just the same way we did other constant acceleration problems. So we can just go through all the steps. The only thing that's different about this is that if you know it's in free fall, then you know what the acceleration is. You don't have to solve for that. So it's a little bit of extra information. So the first thing we have to do is make these four choices. Time equals 0, the instant we're calling time equals 0. The instant we're calling time final. And then we have to choose a position equals 0 and a positive direction. Our time equals 0 and our time final, we need to make those choices based on instance where we have information and instance where we want information. So what do you want to call the instant time equals 0? Yeah, that's the instant that the rock is released. And the stuff we know there is if you drop something, um, it starts out at rest. It starts out with 0 velocity. Um, so we know we're going to be able to come up with the velocity at that instant. We also know, I guess that's about it, isn't it? But we also, we're trying to find a relationship between the height at the water and the height at that time equals 0 instant. And so somehow the position at that time equals 0 is going to factor into this problem. We won't know exactly how it comes up as a variable until we make our choices about position equals 0 and positive direction. And what instant do you want to call time final? The water, yep. Okay, so now we have to do the two that are kind of arbitrary. Um, I always do it this way, so I'm going to do it this way. I put the 0 position at sort of like the lowest altitude thing in the problem. So the water is the lowest thing, so I'm going to put 0 there. And then I'm going to make the positive direction up. And mathematically, there's no reason you have to do that, but I think there is a benefit to approaching every problem the same. You're just a lot less likely to make mistakes, dumb little mistakes. So I'm going to do that. So the 0 position is at the water, and the positive direction is up. And now we can go through and figure out what variables we know, what variable we're trying to find, what variables don't matter to this problem at all for us. Okay, so I'm going to go in order: time final, acceleration, positions, velocity. Yep. Yeah, for the free fall ones, this is just how I always do it. And I don't. I mean, if you do it that way, then it'll be easy to convert between my solutions and my example problems and your work on them. So that's one reason to do it the way I do it. But you could choose a different one. I would just, whatever you do, I would just do it in every problem. Like if you always choose your 0 position to be at where the object is at time equals 0, that's fine. Just always do it that way. Um, no, it doesn't really. Um, and one thing that's nice about it is it keeps all your position values positive. Um, Yes. I don't think there are any problems like that. That's a good question, though. That um, I definitely could do that, but I don't think any of the homework questions have that. Okay, so time final. Do we know like what the stopwatch says when the ball hits the water? Yep. So time final is 1.2 seconds. You know the acceleration? Yes, the acceleration in free fall is always 9.81 meters per second squared down. Our positive is up, so this acceleration is negative 9.81. Do we know the position of the rock at time equals 0? So in this problem, that's the position that we're trying to find. What we know is the position at time final, and we're trying to solve for P initial. So P initial is the thing we're looking for, and P final is equal to 0. Any questions about that? Yes. Squared for acceleration, yeah. Yes, and if you always choose your positive direction up, uh, that's always going to be negative 9.81. And so let me, so say you throw something up into the air on the way up. So this racer is going up into the air. Does it make sense that the acceleration is down as this object is going up, like on the first half of its trip? That's sort of confusing to a lot of people. It does make sense. Like, no matter what the object's doing, its acceleration, if it's in free fall, is 9.81 meters per second squared down. And you can think about it like this. When the thing's on its way up, is it speeding up or slowing down? Slowing down. And when it's on its way up, its velocity is up positive, right? So you have a positive velocity. It's slowing down. So what has to be the sign of the acceleration? Negative. And then what about when it's on the way down? So now the velocity is negative. Is it speeding up or slowing down? Speeding up, so the acceleration has to be down in both cases, negative in both cases. No matter what the object's doing, gravity's accelerating it down. Yep. Well, acceleration and velocity are unrelated to each other. Think of it as they're independent of each other. So no matter how fast you throw it, that that's not saying anything about acceleration. Um, so you can throw it 1,000 miles per hour up. It's still accelerating down at 9.81. So gravity is still making it slow down. It's just starting at a faster value. And it'll take longer for gravity to make it stop and then turn around and come back down. Any other questions? Okay, so we got P initial, that's the thing we're looking for. We know P final. We know the velocity at time equals 0. Yes, you can tell because I'm writing it here. And then velocity final. Do we know the velocity right before it hits the water? No, we don't know that, but if we can solve this problem without it, that's fine. Okay, so this is what we have. And now we're looking for one of these three constant acceleration equations that'll let us solve for PI, and everything else in it will be known. So here are the three equations. V final is equal to V initial plus A times T final. And then P final is equal to P initial plus V initial times time final plus 1/2 A times time final squared. And then the last one is 2A times the quantity P final minus P initial is equal to V final squared minus V initial squared. Okay, so can you see any of those three equations that work with the variables we have? The second one, yep. So this one works in this problem. So we have 2 times negative 9.81 meters per second squared times the quantity, PF is 0, minus PI, that's what we're trying to find. I'm doing the wrong one. Okay, second one. So P final is 0. That's equal to PI, which we're trying to find, plus 0 times 1.2 seconds. So that term's going to be 0. Plus 1/2 times negative 9.81 meters per second squared times 1.2 seconds squared. So I'll write this as negative PI is equal to 1/2 times negative 9.81 is negative 4.905 meters over seconds times seconds times 1.2 seconds squared is 1.44 seconds times seconds. You can multiply both sides by -1 and you get the PI is equal to positive of all this stuff. And so PI, the cancellations, the seconds all cancel. And so you get units of meters, which is good. That's what you want for a position. And you get a value of 7.06 meters. Yeah, actually, so I'm going to say that, get that in your notes, put it in sort of like a formal little block right now. But anytime you just drop something, it starts with a 0 velocity. It turns out that the real like full rule is if you drop something, its velocity at the instant that you drop it is the same as the velocity of whatever you drop it from. So if you're in a car and you open the window and drop something out of the window, just at that first instant that you drop it, it's going horizontally at 55 miles an hour. And then air resistance and gravity take over and make it, do different things. But if you drop something from a bridge or a building, those things have no velocity. And so when you let go of those, the velocity is 0, just at that instant. Well, actually, it's true. It's true for free fall problems. It's also true even if there's air resistance. So like if you take a balloon, driving down the highway, pull the balloon out the window and let go of it. right at that instant you let go, that balloon's going 55 miles an hour. But very quickly, I mean, you can imagine what this would be like. Air resistance grabs hold of the balloon. It has a very small mass, a big surface area. It's going fast. And 1 second later, it's going close to zero, you know. Um, but at the instant you release it, it'll be going the same velocity as the car. Any other questions about this problem? Um, okay. So now here are two important facts about free fall problems. The first one is what I just said. Um, if an object is dropped, then at the instant it's dropped, at the instant it's released, it has the velocity of whatever it's dropped from. Okay, so if you drop something off of a bridge, it has zero velocity when you let go. If you drop something in an elevator, that's, say you have an elevator that's going down at 3 miles per hour, 3 meters per second or something, then at the instant you let go of it, it has a downward velocity at 3 meters per second. This is not true if it says that something's thrown or launched. That's different. Okay, but if it's just dropped, if something's holding it and then lets go of it, at that instant, its velocity is the same as the vehicle it's in when it's dropped. And then the second fact that we're going to use a lot is if an object is launched up, then you know what's going to happen. It's going to go up, slowing down until it comes to rest for an instant, and then it'll start coming down, speeding up. Um, so if that happens, the highest point in the object's path occurs when its velocity is equal to zero. Okay, so you can always use that to specify when an object gets to its highest point. And we'll do a problem that uses that right now. But the idea is, so as something's on its way up, it starts out with a high velocity up, positive, and it's slowing down, so it's getting smaller and smaller positive velocity until finally, just before it switches over to negative velocity, it has that one instant where it crosses over from positive 0.00001 meters per second to negative 0.00. In between those, it's zero. And you can use that to find where that point is. Okay, so here's another example. Let's say that a ball's thrown up into the air. From a height of 3 meters. With an initial speed. So the instant it's launched or thrown, its speed is 10 meters per second. And we want to figure out a few things about its motion. So the first one is, how high is the ball at its highest point? And then the second thing is, what's the ball's velocity instant when it returns to the height of 3 meters? Okay, so let's start with those two. So what's going on here? Here's the ground. There's like a step ladder on the ground. There's a person standing on the step ladder. Those are long arms. The person threw the ball up into the air. The distance between where the ball was released and the ground is 3 meters. Like I said, I'm almost always going to choose my zero position to be the ground. So I'm going to just draw that here, and I'm going to make my positive direction up. And so based on that, we know that the position where the ball is released from, if you go 3 meters in the positive direction from zero, you're at position 3. And the ball is going to go up, reach its highest point, and then come back down. We're trying to figure out the height at this point here. Okay, so let's first these 4 things. So first, what do we want to choose as our instant where time is equal to 0? Yep. And the reason we want to do that is we have information there. We know the height of it. We know the speed of it. We can turn that into positions and velocities. And then what about time final? when it reaches the highest point. And I want you to notice there's something new in this problem that I don't think we've seen yet in an example problem. We're going to have to choose a new time final when we go on to part B, because for part A, we're trying to calculate a position when the ball is at the highest point. But when we do B, we're trying to figure out a velocity at a different point, and you can't solve for something at an instant that isn't one of your chosen instants. So for part B, we'll have to come back and change that. Zero position is the ground. Positive direction is up. Anyone have any questions about those? And now we can think about what we know and what we want. You know the elapsed time between when time is equal to 0 and time final? No. But if we can solve it without that, that's all right. We're not asked for it. We know the acceleration. It's down, so since positive is up, this is negative 9.81 meters per second squared. Okay, so negative 9.81 meters per second squared. Is that the acceleration when the ball's on the way up or when the ball's on the way down? And yes, everybody's right. But remember, so that is the acceleration no matter what's happening. If the thing's in free fall, what changes is the velocity. The velocity on the way up is positive, on the way down it's negative. But the acceleration, gravity's always just pulling down on it. And that's what gravity is always doing, is making an acceleration down of 9.81. Okay. Do we know the initial position? Yep. That's at positive 3 meters. Do we know the final position? Do we want it? That's what we're trying to find. Do we know the velocity at time equals 0? We weren't exactly given it, but we can figure it out from what we're given. So the magnitude is 10 meters per second, because that's the speed. And now we just have to think about the direction. At the instant time equals 0, is it moving in the positive or negative direction? Positive, it's going up, so this is positive. And then do we know the velocity at time final? Yep, so that was one of those two things that I said, this is going to be useful in free fall problems a lot. At the time that the object reaches its highest point, the velocity is equal to 0. So this is 0. Of the three, yes. It was given in the problem that, so it has an initial speed of 10 meters per second. And so all you need to do is come up with the sign corresponding to what direction it's moving. Okay, so is there a constant acceleration equation that works with this? Third one, yep. So we're going to use 2a times the quantity pf minus pi is equal to vf squared minus vi squared. So we have 2 times negative 9.81 meters per second squared times the quantity, P final is what we're trying to find, minus 3 meters. And that's equal to V final squared, so 0 squared, minus quantity 10 meters per second squared. So that's negative 19.62 meters per second squared times the quantity PF minus 3 meters. And that's equal to, so first we square 10 meters per second, and that gives us 100 meters squared per second squared. And then the negative is outside the parentheses, so that's still there. Right now, we might as well just multiply both things by -1, get rid of the sign. And then I guess now I'll divide both sides by 19.62 meters per second squared. So we have PF minus 3 meters is equal to 100 meters times meters over seconds times seconds divided by 19.62. We have meters now in the denominator and seconds times seconds in the numerator because we divided by this. And if you divide that out, you get, I guess I didn't do it this way before, you must get 5.08. And if you cancel out the units, 1 meter cancels, all the seconds cancel, and you get an answer that's in meters. And now you can just add 3 meters to both sides, and you get that the final position is 8.08 meters. Any questions about that? Okay, so now we're going on to part B. So part B is asking, what's the velocity of the ball when it's thrown from a height of 3 meters, goes up, reaches the highest point, 8.08 meters above the ground, and it comes back down, and at some point it's going to cross that height that it started at. And we want to calculate the velocity of the ball at the instant that it returns to that starting height. Okay, so let's think about these 4 choices. These two, the position equals 0 in the positive direction, I'm going to keep those the same. But what about the other two? I mentioned before that we're going to have to change something. Is there any reason that we have to change our time equals 0 instant? No, that'll still work. I mean, we still have a lot of information there. Let's keep that one the same. So that means the one that we have to change is the time final. And that's because one of our instants has to correspond to the instant where we want to find stuff. And so our time final is going to be the instant when the ball returns to a height of 3 meters. Okay, so now let's go back through the list. Do we know time final? We're not given anything like that, so no. Do we know acceleration? Yep, nothing changes about that. It's still in free fall, so negative 9.81. Do we know the position at time equals 0? Yep. Do we know the position at time final? Yes, I'm writing it. That's 3 meters again, right? We're looking for when it returns to that same position. Do we know the velocity at time equals 0? Yep. So V initial is positive 10 meters per second. Do we know the velocity at time final? That's what we're trying to find. Okay, so is there an equation that works with these? Second one again, yep. So we're going to use 2a times the quantity P final minus P initial is equal to VF squared minus VI squared. So we have 2 times negative 9.81 meters per second squared times the quantity 3 meters minus 3 meters is equal to V final squared minus the quantity 10 meters per second squared. And you can see 3 meters minus 3 meters goes away. And so all that stuff on the left side of the equation goes away. So we get that 0 is equal to VF squared minus 100 meters squared per second squared. And in other words, VF squared is equal to 100 meters squared per second squared. So VF is equal to, and I'm going to leave a little space here, it's equal to 10 meters per second. What goes in that space? There's something important missing here. Well, yes, it is going to end up being negative. The thing I was thinking of was plus or minus because you took square root. And now you have to think physically about which so physics answers are never going to be this or that, you know. There's always going to be one answer for these problems. So you have to think, what do we know that's going to let us determine whether it's positive or negative? And yeah, what we know is we know physically that the one we're looking for is when the ball's on the way back down. So we know the ball has whatever sign corresponds to down. In our case, we said positive was up. So when the ball's going down, it's negative. And so the final velocity is negative 10 meters per second. Yes. Because it's multiplied by 3 meters minus 3 meters. So it's multiplied by 0. So now that's the thing that I want you to notice now. So we did this problem. It's an example of the kind of problems you're going to do. But this is kind of a interesting intuition thing. The left side, so we got that the speed at the end was the speed at the beginning, just the signs were switched, because the left side went away. Okay. It went away, and then these two things were equal to each other, and that's how we got that the speed at the end was the same as the speed at the start. And this didn't really exactly go away because it started and ended at 3 meters. It just went away because it started and ended at the same spot. If you look at this equation, if it started at 15 meters and ended at 15 meters, this would have gone away just the same. Okay, so if you launch something up into the air, the speed when it returns to that height is always going to be the same as the speed when you launched it. And the velocity is always just going to be, opposite the velocity when you launched it. Remember that these equations depend on the free fall assumption that air resistance is negligible. But still, this tells you, like you hear people, I don't know, maybe you don't hear people say this that much. I remember actually there was like a hurricane in Florida like a year ago or something, and there was like a public service announcement requesting that people not fire their guns at the hurricane. So like on New Year's Eve or whatever, like people like shoot guns up into the air. And this tells you why that's a bad idea. So if you shoot a bullet, it's going really, really fast. So there's a ton of air resistance. So this equation doesn't exactly apply, but it does give you the idea that if there was no air resistance, when the bullet, so you shoot the bullet at the time that it returns to the height of that you shot it, it's going to be going just as fast as if you just shot it like that towards the ground. In real life, it won't be quite that fast because of air resistance, but it's going to be going really, really fast. And so you don't want to do that. Or if you do it, you want to shoot straight up and go somewhere else. Okay, let's do a part C. And why don't you try to do it? Work through it with each other. Ask me questions if you get stuck. But let's figure out now what the velocity is going to be of the ball just before it hits the ground. So this is pretty similar to part B. But what do you think is going to happen? So it's going to go past a height 3 meters. Gravity is making it speed up. There's no terminal velocity or anything like that in the free fall problems we do because terminal velocity depends on air resistance, and we're assuming that there's none. So we expect that just before the ball hits the ground, its speed is going to be a little faster than 10 meters per second, and its direction is still going to be negative down. Okay, so see if you can work through that and compare answers to each other and let me know if you need a hint or something. Okay, so time equals 0. We can still use the instant it's thrown. Time final is going to be the instant it hits the ground. Position equals 0. I'm going to choose the ground. And the positive direction, I'm going to choose up. We don't know time final. We know acceleration. Initial position is positive 3 meters. Final position this time is 0, because we're looking for it to hit the ground. Initial velocity is positive 10 meters per second. And then we want to find the final velocity. The equation that is going to work is the same one as for the last two parts. So we have 2 times negative 9.81 meters per second squared times the quantity 0 minus 3 meters is equal to v final squared minus the quantity 10 meters per second squared. If you multiply out all the stuff on the left side, you get positive 58.86 meters squared per second squared. And on the right side, you get VF squared minus 100 meters squared per second squared. Then you can add 100 meters squared per second squared to both sides. So you get 158.86 meters squared per second squared is equal to VF squared. And now take the square root of both sides. You get VF is equal to, the magnitude of that is 12.6 meters per second. But don't forget, whenever you take a square root of a variable, you have the plus or minus. And so now, to figure out whether we want the positive or negative, we have to think physically about what the object's doing at the instant that we care about. So which one do we want? Negative, because we're talking about the object going down. By the way, there always is a physical meaning to the other answer, even though we'll discard it. So let me show you what that means. If you plotted out position versus time graph of this motion, so there's position, there's time. At our time equals 0, the object is at 3 meters. And we know that it goes up to a maximum height of 8.08 meters. And the graph would look like a parabola, like that. But mathematically, that parabola doesn't stop when it hits the ground. This equation just thinks the thing goes on forever, and it also thinks that it went on forever before. Physically, we're never going to deal with negative time, so none of this stuff, we're never going to have answers where the time is negative. But this final velocity of negative 12.6 says that right here, when we get back to a position of 0, the slope of that parabola at that point is negative 12.6. Okay. And if you look on this parabola at the point where you can think of this ball as coming up through the floor back here at some negative time, the slope there would be positive 12.6 meters per second. And so basically, the positive one of those, the one we discarded because it wasn't relevant to our question, is saying what would the velocity be of the object that's on this trajectory at the instant that it came up through the height of the floor over here. So anyways, there are always sort of pseudo-physical meanings for all of these answers, the ones we keep and the ones that we reject, like in this case, the positive velocity. And that's sort of what it relates to. Any questions about that one? Okay, well, so for lab this week, all we're doing is that lab test, and you can do it tonight or Wednesday. Either one's fine with me. Let's do it in here, though. I think it's more comfortable to take tests at these desks. So let's just meet back here at 7:30 and start the test.